Hello everybody. I'm Tessa, and this is a talk about pattern synonyms. Now, the prerequisites of this talk about pattern synonyms is first you need to know pattern synonyms, and then you need to know some basic dependent type theory, and you need to know the notion of definitional equality in the context of dependent type theory. And mm, let's look at type theory and doing mathematics in type theory. It is good because the computers can help us to simplify some of the proofs by just doing reduction, and some of these reduction can reduce huge terms into smaller ones. But and we all like this feature. But what about real world mathematics? In that case, we work with abstract structures. And in type theory, we use records to simulate those abstract structures like groups and categories and stuffs. But when we are working with those structures, we don't know the reduction rules of those abstract record fields. For example, when I prove a lemma about a group, I don't know, so I have to do manual rewrites on the group identity rules. But actually, most of the implementations of groups satisfy one of those identity rules by computation um, or by definition. So by abstracting things, we lose the ability to simplify something by reduction. So how do we fix this? Um, an inspiration is from cubical type theory, where there is a type called the path type. The exact mathematical meaning does not matter, but the definition is like this. We have a path type, it's path A and the smaller a, B, and this is a type, and the small a and the small b are instances of the type A, the capital A. And this type, is like a wrapper of a function from a type called I, called interval, to A, and satisfying two extra reduction rules that when P is applied by 0, and 0 is an instance of interval, then this function must reduce to the small a. And when applied by 1, it must reduce to small b. Um, so this is the idea of path type. It is basically a wrapper of a function such that the function must satisfy two rules. And when using an instance of a path type, we um, even we don't know the instance of the path type. It is an abstract parameter. We still can assume these reduction rules and reduce when working with the abstract parameter. So we can view a path in this way. So path is a function satisfying some definitional equality. It is a wrapper of a function. So we can put it into a record. Here is a record with only one field. One field is called at, and it is a function from interval to dependent type A. Here I just made this definition heterogeneous. You can also make it, I just made it dependent. You can make it non-dependent to simulate um, this definition, but this doesn't really matter. Um, but this is just a wrapper. We also need it to satisfy the definition rules. So we um, um, we think of path as a record with this field, along with extra restriction that this field must satisfy these reduction rules. Like the at, when applied by left, it has to reduce to small a, which is the parameter. And when applied by right, and left and right are just aliases of 0 and 1. And mm, And so this is another perspective to view the path type. And and these pattern matching syntax is actually used to perform the reduction, because we have a pattern matching syntax for normal function reduction, and we use the same thing to perform these kind of abstract record reductions. And we can generalize this little piece into arbitrary types. So we can we can make this structure into any record with any partial pattern matching. So let's look at this structure. This is a monoid type on natural numbers, and it has uh, a operator and a left identity rule, a right identity rule, and a associativity rule. Um, and so, for example, we can make the left identity rule a reduction rule on the on one of the field on the operator. And then this rule holds by definition on the record. So we just like, so if we implement the path type, maybe we can reuse the path type facilities to do something like this. And by doing this, we can have some reduction rules on abstract monoids. But this is not very useful because this definition is specific to natural numbers. Usually, we define the monoid type for arbitrary types and the arbitrary unit element. So look at here. These natural numbers, we need to replace it with an abstract type, and these zeros, we need to replace it with an identity element to actually imitate what we're doing nowadays. And this is what we want to do. We want to generalize this struct with two parameters, the type and an instance of the type A, which has to be a pattern synonym somehow. And so it is a pattern synonym, so I can put it in a place where I write pattern matching. And and when I use this monoid type, I can the compiler knows that when the monoid operation is applied by the unit element, which is also another abstract property, it reduces according to the reduction rule written there. And with more features like overlapping pattern matchings, maybe I can do something else, like writing two of the identity rules at the same time. So I have both of the identity rules by computation, which simplifies theorem proving relevant to abstract monoids. So this is what we're expecting. We want the unit parameter to be instantiated as a valid pattern, as a pattern synonym, so we can put it at the left-hand side of a pattern matching. And we also want, so there's a typo, it should be the dot there. We want the unit element of M multiplied by some other thing reduced to Y, as we said in the reduction rules. And this is not implemented in the language we're showing. So this is why there are errors out there. And what we're asking for here is, so if we want to recover the reduction rules in abstract structures, we need partial pattern matching and relevant reduction rules in records. And we also need record fields with these pattern matchings. And yeah. And we also need abstract pattern synonyms, which means when we apply a function, we also need the abstract pattern synonym means the record parameters such that they are required to be pattern synonyms and they can be put into pattern matchings. And we also need function applications where if we see a parameter which is required to be a pattern synonym, we actually check the argument to be a pattern synonym. So the arguments must be type checked with respect to the criteria of pattern synonyms. And by that, we actually implement something that allows us to pass a pattern synonym around and put it into pattern matching, which is abstract over these reduction rules. And there are something else we may consider, for example, the semantic interpretation of this feature. Maybe there are more use cases, and maybe there are some counterexamples that prove this to be useless or doesn't make sense. And so that's basically what I want to say today. Any questions on this idea?
don't see any online questions yet.
Um, yeah, I was wondering if you could characterize the pattern synonym in terms of uh, some other type of so there's hypernyms in where it's something more general and or hyponyms, which are kind of more specific examples. So can you take a pattern synonym and substitute this exactly for in a occurrence, or it's a and what is the complexity of this equivalence decision procedure? Thanks.
So a very basic example will be the monoids, the standard monoid definition on natural number and addition. So basically, we instantiate this monoid with natural numbers and zero. The zero itself is a constructor, so it is a valid pattern synonym. And it substitutes the pattern matching left-hand side to make it the same thing as this definition. But we can also specialize it to other types. For example, integers and something else. Did that answer your question? Is that a good example? No more questions?
Um, okay, maybe. So I once tried to do something similar, but with arbitrary rewrite rules basically in a record. So, but so I ran into a lot of problems with the meta theory of that thing because you get a lot of non-confluence issues when you try to do that. So have you done any meta theory on this yet, or
Uh,
is that
I don't
something
think
you
so.
want to do?
I don't think so.
Like if you want to, or yeah,
Yeah,
want to
I
prove
just
even just subject selection for this.
yeah,
Yeah.
I don't know. Basically, this is a result that I have realized when I was messing around with some features relevant to partial reduction rules and pattern synonyms, and that's what I. So I believe that it can solve the problem that abstract records does not have reduction rules.
Right. So it feels like the extra restriction that you have here, that the fact that it has to be patterns, might be enough to work around the problems that I had. So it's very interesting, but yeah, I was just curious. Yeah. Okay. Cool.
Thank you.
Thanks very much.